But his military strategy fails to consider a force much stronger than any of the barbaric tribes: the climate.
Let's imagine we're in the year 535. The eastern provinces of the Roman Empire are doing fine. They have a new upstart emperor who was born in the western provinces, who speaks Latin as his native tongue, and has a dream to reconstitute the Roman Empire. And he targeted as his first goal to reconquer Africa. Africa fell almost in a matter of months. The Roman Empire had reconquered the richest breadbasket of western half of the Roman Empire and was poised to now move on Italy. In 536, they cross from Sicily into the mainland of Italy and start marching towards Rome. And they're marching up successfully in the spring of 536 when something entirely unexpected happened. The sun stopped shining for a period of between 12 and 18 months. A contemporary says that at noon, the strength of the sun was about like that of the moon.
What could have made the sun stop shining in the spring of 536 AD? Was the constant darkness why Justinian failed, when the whole empire seemed within his reach?
Switch to,
At the University of Maine, scientists have identified physical evidence of how the climate was shifting at the same time Justinian set out to expand the empire.
When there's a small iron peak, but a much higher sulfur peak.
A unique team of climate specialists and historians has come together to study how a natural climate event could have brought down the Roman Empire. This large freezer inside a University of Maine lab holds an ice core, which offers insight into what happened in the 6th century.
This piece is about 60 meters deep. We keep it in our freezer at temperature minus 25 Celsius. And right now, I'm preparing this ice for laser ablation analysis. I'm scraping the top part off to remove any contamination and make the surface flat as possible.
This ice core serves as a record of the climate in Europe for the last 4,000 years. Scientists retrieved it from a mountain peak on the border of Switzerland and Italy, in the heart of what was once the Roman Empire.
Up until now, most of the great ice core work has been done in Antarctica. There, the technology is perfectly adapted to ice cores that, as in Greenland, are 3 kilometers long. In Europe, the situation is completely different. The ice core from today to bedrock is 72 meters. And the technology was not yet established, which would allow one to see patterns in ice that was so heavily compressed. The Climate Change Institute under Professor Majewski has perfected a new instrument which allows one not to measure 100 times in a meter, but up to 40,000 times.
The remarkable thing about this instrument is that it uses a laser to collect the sample, and you can actually see it on the screen here. It almost looks like a worm moving along. What it's actually doing is like a tiny jackhammer poking away, flaking off chips of the ice. Once those pieces of ice fly off, they get incorporated in a gas, and that gas then takes the sample to this instrument, which is capable of measuring very, very low concentrations of things like copper, lead, sodium. Every single one of these has a different story about the climate, about human activity, a variety of things.
Once they've identified the area of the ice core that corresponds with the year 536, scientists find a higher level of sulfur than is normal, evidence of a volcanic eruption. They also find volcanic glass dust in the core sample, which allows them to locate where the eruption took place: Iceland. But would this volcano have been enough to stop Justinian's military campaign?
Determining the magnitude of the eruption is hard from an ice core, except if you take a look at the sulfur, the bismuth, and the tin levels, they're remarkably high for the last 2,000 years. So that would tell us that the 536 was a very big event.
The eruption threw so much sulfur dioxide into the atmosphere that in the years following, temperatures dropped by about 2 degrees, one of the coldest periods of the last 2,000 years.